Again, welcome to the seminar. Dear friends, today we have speaker Renzo Ricca, who will tell us about topological cascades through vertex reconnection. So please.
Thank you very much. Thank you to everybody, and thanks to the Novosibirsk group for inviting me for this talk. It's a great pleasure because I have fond memories of my visit to Alexienko's group at the time, and well, only a few years ago. And I am very happy to give you some information about progress on vortex reconnection and cascades. So the motivation for this talk are, let me go to the first slide, is to determine a long-standing problem, to determine relationships between structural complexity, in particular physical knots and energy. For physical knots, I mean in this case vortex structures, and quantify energy and helicity transfers in dynamical systems. For this, I'll show you how to introduce new techniques based on the use of knot polynomials and extend and apply new topological techniques to study complex systems. Since the audience is probably quite well informed about vortex dynamics, I will skip backgrounds, but I will dwell on aspects of reconnection, at least for graduate students or for young postdocs, is useful to know before getting into the topic of knot polynomials. For simplicity, I will refer to a physical tangle made of a network of filaments and filamentary structures in 3D. And as you know, this is a big problem in terms of understanding stages, later stages of turbulence developments and transition. A group in Onera in Grenoble, 74, collected in the beautiful book of Van Dyck. And here you see the transition from a laminar flow to a turbulent flow, where is visualized this vertical region. Well, this has been confirmed by lots of numerical simulations, and this is just a picture of one of the last ones, where tubes, filamentary structures, are seen to play an important role. That's why we focus on filamentary structures, and allow me to give you a very, very simple model just as a reference for our...
Excuse me, Renzo. Filaments are laminar or filaments are turbulent?
Filaments are laminar in my talk. So they are thought to be present in a background fluid, but they are, in my talk, they are considered to be kind of, well, relatively speaking, stationary solutions. Although we know very well that they are not steady at all, they deform, etc. But as a model, I don't think of, say, decomposition of velocity fields in a mean field and average oscillation. So I'm thinking of average quantities all the time. So this is just a model, an idealization. We have a tube made of axis C. It's cross section. We take it for simplicity to be very thin, very small, and essentially circular. The volume V of the tube, and then we embed this tube to form a knot in a three-dimensional space. Here we have an example of a link, and the knot or link we refer to is just the physical support of a vorticity omega. Again, for simplicity, we imagine that each tube, each tubular knot is foliated by vortex lines, and the essential property here is that vorticity is as a zero normal component on the boundary of this tube, so that the tubular boundary is a material surface. As I said, this is just the preliminary information to understand what is going on later in the talk. So the vortex tangle is just the union of these knots and links that are made by vorticity. And in ideal condition, it's worth remembering that the strength of this tube, i.e. circulation, is conserved as well as topology is conserved. Of course, we all care about the changes of topology due to reconnection and viscous effects, and I will consider the change of topology to some extent, but I won't consider viscous dissipation in my talk. It's also important to remember a quantity that has a topological significance in fluid mechanics, and that is helicity. Helicity for a tangle is just the integral of u dot omega, u being the velocity field, over the volume of vorticity. And this eventually is extended for localized fields. This is an important assumption. Localized fields, meaning a tangle of vortex filament where vorticity is localized on these tubes. In topological interpretation of helicity is rooted in the famous celebrated work of Moffat, 1969, where helicity was expressed in terms of Gauss linking numbers, LKIJ, which is a measure of the linkage between tubes I and tubes J. With Keith, we extended this result to include the self-linking number, which is also a topological quantity that comes from the complexity of the vortex lines within the tube and the tube embedding itself. So here I expressed helicity for localized fields. Well, in that case, we have the gammas, the circulation of each tube, and these two quantities, the self-linking number of each tubular knot and the linking number between tubular knots. And in case of localized fields, and in case of tubes that are very thin, then we can eventually reduce this expression to this form, simply because omega, we can take it as a uniform distribution on the cross-section, say, so small that can be integrated out in this circulation. So we are left with a contribution of U along the axis of these tubes. Well, the linking number is just due to Gauss and is measuring the linkage between tubes. And in the particular case of the picture is a Hopf link, and there is a negative crossing here. So is -1 the result. The self-linking number is due to work of Calugariano extended by White and can be decomposed in two contributions, the writhing number and the total twist number. It's very important to remember these two decomposition. Remember, self-linkage is topological in character, whereas is made by these two quantities, whereas writhe and total twist are geometric in character. So two global geometric quantities that sum together give a topological quantity. Writhe, without any formula, is just a measure here of the folding, of the coiling of the filament in space. And by C, I mean, if you like, the baseline edge of this ribbon. And the twist is a measure, you see here, C and C star. So you see, writhe is a measure of a geometric curve in space. Twist, however, is a measure of there is some thickness of a ribbon. We refer to a ribbon, so is related to the winding of one line with respect to the other. So you may imagine the baseline of this ribbon and the C star, the push off, if you like, or the parallel line in the black as the other edge of the ribbon. Or alternatively, you may think of C as the axis of our tube and C star any field line that is winding around the central axis. So this is very important for the rest of my talk. Okay, and now I have a few pictures or a few movies because Lou Kaufman's talk suggested me to show you again this beautiful experiment by Lim. And I give it a different reading of this experiment, which is very beautiful. I'm going to show it in a moment. You see the title, Topological Cascade. So there are two vortex rings you will see in the movie, one red and one blue, that are colliding one against the other. And after collision, you see that immediately there are a number of reconnections and little ringlets formed as a result. Now, of course, we have an immediate cascade of topology from two big rings to a number of small rings, simply because reconnections take place due to the symmetry of the system instantaneously at all points around the rings. Now, time to show you the picture, and this is it. So you see the Reynolds number is in water. You see the shot of the two rings and the formation of two ringlets is, of course, very beautiful because you can see, I'll show it again, you see immediately the transition from one or two big topological structures to small structures. And of course, it's important to understand what's going on in terms of reconnections and topology. And so I'm also pleased to show you the movie of the experiment done by the group of William Irvine in Chicago about the production of a trefoil knot in water and further evolution of this structure. Now, if we observe, there is this airfoil made in the shape of a trefoil knot that as a result produce a vortex knot, a vortex filament in the shape of a trefoil knot. And then if you follow closely this evolution, you will see that the filament strands at certain point will reconnect and the structure will form other structures like the ones we see it now that analyzed show to be a hop link, and then further reconnections down to two separate just visible rings and then down to full dissipation. So before moving to consider topological aspects, I like to dwell on the reconnection process itself, because I think is very important in terms of these factors that I showed you before, writhe and total twist, because of course, as I said at the beginning, we are keen on understanding the energy production and the energy transfer. And so it's...
just
yes,
one question.
Yes.
Do you have an energy of reconnection or it costs something or it's just not?
No, it costs something. It costs something all the time. There is a reconnection, and the energy has two facets, if you like. One is that there is an energy cost, and that is due to dissipation. Although I mentioned the ideal conditions I worked in, I'm keen to, to underline that the viscous effects, dissipation effects, or if you like, in magnetic system, resistive effects, and in other contexts, like quantum fluids, this costs something. On the other hand, there is not only the issue of energy cost, but there is also the issue of energy transfer. All the time we have a reconnection, we have a change in the scale of the structure. So there is a kind of scaling law that brings us from large structure to small structures, down to evanescent structure. And at each stage, there is not only an energy cost, but there is also an energy transfer of the remaining part of the energy through reconnection. Okay, so this is the reconnection experiment done by the group of Professor Alexienko, exactly at Novosibirsk, and I'm very, very happy to show this movie. I did show this movie to many, many people around all the time I had the opportunity, because I think is truly remarkable, and I have a chance here to also say hello to Pavel Kuibin, a good friend of mine. Now here we see the vortex filament that are approaching, and they are modifying their mutual angle of inclination, and they reconnect. It's a very great piece of information from this movie, and I'm happy to show it again. You see here the filament strands are approaching, and if I stop the movie here, you see that they are almost at an orthogonal angle. But then as they get closer and closer, they modify themselves to get to what we will say anti-parallel. And then look at the little, you know, the little frames, oh, I'm sorry, I want to go back. The little frames, just when they are in an anti-parallel condition, you will see that in the few frames, they are counter-rotating, one against the other. And then there is a merging, and then there is a separation. Now, I want to spend 10 minutes at, say, graduate level discussion, but with insight of my experience over the years, not to propose a model of reconnection, which is still undergoing, but just the mechanics of vortex reconnection, at least until the moment where viscous effects can no longer be neglected. And in order to understand the mechanics, we have to start with the Biot-Savart induction law. And this is due to simply the induction of the vorticity, which, remember, in our case is localized in tubes for simplicity. This is ideal version, say, before reconnection. And vorticity confined in this region of the vortex tube induces the velocity. And I assumed here that I focus only on the velocity due to vorticity, assuming that the other contributions from velocity, say from, you know, from translation, rigid translation, or other forms of contributions are neglected. Now, if I develop an asymptotic theory following Bachelor, chapter 7, in Bachelor's book, and actually, as I pointed out a long time ago, was developed by Levi Civita in Italy in 1905. Well, we can express this Biot-Savart induction law in local terms plus a global contribution, and the global contribution remains finite. But if we approach the vortex tube, so if we are very close with X, going very close to the tube vorticity, then these contributions is made of two parts, one given here and the other one given here. And rho denotes the distance from the axis, e theta, the azimuthal vector on the axis of the tube. And there is this term that contains the radius of curvature times this log L over rho. L over rho, we can take it as independent from time, and it actually can be considered indeed as a constant. What is important here is to observe the effect due to binormal contribution. So in other words, we can express the rotational velocity due to vorticity as made of two contributions. One, the theta contribution, gives just circulatory motion of flow around the vortex without creating any drift velocity, any translation of the vortex in the fluid. And the other one is the binormal contribution, which is responsible, at least locally, for the motion of the vortex tube and is proportional to curvature. Okay, so we take our tube, and we put a reference frame on it, tangent, normal, binormal. We take the vorticity in this point aligned with the tangent, and here we have it. And then these two contributions are simply given by a rotational contribution around the cross section of the vortex and the drift velocity due to the binormal. I want to spend a few more minutes just working on these two contributions at an elementary viewpoint to understand what's going on for reconnection. Well, azimuthal contribution, let me focus on this one first. The azimuthal contribution U theta can be made, can be distinguished in two conditions. One is when we have parallel vorticity. The vortex tubes are aligned with vorticity parallel. We may have different circulations or equal circulations. And what you see here are the streamlines around these cores of vorticity that are coming out of your screen. And the streamlines are going around. So the flow goes around both these cores, independently from the relative strength. Evidently, if one of the strength is much greater than the other, is going to drag together the smaller core or the less intense core. So here we have a simulation done by Josserand and Rossi not long ago, and it sees is a cross section. So it's basically a cross section of two straight tubes, and in red is vorticity and is color coded according to intensity. As you see, being parallel, they merge together in this fashion to form one single structure. There is no reconnection here. In order to have reconnection, remember, the filaments must move one against the other, so the UB term must be present. Let us consider the other case where we have contribution, so straight tubes, but antiparallel vorticity. Okay, antiparallel vorticity, these are the streamlines. We may have different circulations present, and with different configuration of this pattern, you see here at the central point on the axis of symmetry in a very high strain due to the contribution of each streamlines at this point. Okay, well, in undergraduate calculation, we have here a zoom in of this picture, an enlargement of this picture, and in a P at the central point here, we have a contribution from both fields coming from both vortices, so we have to add up these two circulatory contributions. Okay, now I give you a very simple proof of antiparallel condition. Assume for simplicity that the vortex cores are not yet totally close to one another, are very close but not completely close, so that we can still well ignore viscous dissipation. And so I'll use for this simple-minded proof the Bernoulli theorem. I put here my point P, and I use Bernoulli theorem that says that the pressure at P plus contribution from kinetic energy density is constant on the streamline. Then I do a little bit of geometry. I consider two elementary elements, two elements of these vortex filaments approaching this point P. They get together because they are oriented with a curvature, with a binormal contribution that are moving the strands one against the other. So they have a curvature made so that they can move one against the other, and this azimuthal contribution one with respect to the other. And by simple geometrical information, we have since here velocity must be at the maximum and the pressure goes to the minimum, the maximal condition for the velocity is attained when alpha from geometric configuration is 0. And that proves that these two arrows being alpha 0 must be in oppositely oriented directions. That proves the fact that they must be anti-parallel to optimize the process. Of course, is an optimal situation. Reconnection may take place when they are close to anti-parallel situation, but remember what we saw in the movie. In the movie, we saw that they were orthogonal, they were with some curvature, so they are still pushing one against the other, and at a certain point, they get anti-parallel and counter-rotating, exactly as I showed you in this streamline pattern. Now, there is a reconnection stage where viscosity plays an important role, and we see here still some very weak vorticity that is stretched away as they reconnect and they move apart. They move apart again because their local curvature is such that the binormal component makes them moving away one another apart. And here is one of the recent simulations done by the group of Fazil Hussein, the vortex tubes. At a certain point, they get close together, they merge. There is this bridge structure of a weak vorticity form that still survives for some time. These tubes do not show any structure inside. And this is, of course, next step for all of us in terms of experiments, in terms of numerical simulation, and of course, in terms of analytical model. And this poses a very, very difficult questions. Now, let me pause for a moment to consider a result that I believe is important in this context. We can prove, Dewitt, Sumners, Christian Lang, and myself, we proved writhe conservation in terms of anti-parallel reconnection. And the proof is based on assuming that the axes of these tubes are modeled by polygonal curves. I won't discuss the proof because I noticed that Dewitt Sumners is going to give a talk next week, and I'm pretty sure that he will spend some time on the discussion of this mechanism that is relevant in many contexts, not only in vortex dynamics. So I leave to him the mathematical proof of this statement. I just give you a very, very sketchy idea of the process. Well, if we are going to be in an anti-parallel condition, then assuming polygonal curves, we have to think that these segments are going to approach each other closely, at a certain point annihilate. And by annihilation, they leave any writhe, if there is a writhe present, that there is one in this particular projection, unchanged. So the local, the writhe helicity, the writhe during reconnection remains conserved under anti-parallel reconnection. And this is the statement of the theorem that Dewitt Sumners will discuss. The writhe of the strands before reconnection is unchanged, remains conserved, and is equal to the writhe after reconnection. Well, we can extend this to including circulation, assuming that circulation are the same, the circulation of the two tubes or the two tubes with axes A and B are the same. We can extend this immediately to writhe helicity, saying that writhe helicity remains conserved. but we know that helicity is not conserved under reconnection. So since helicity is made of linkage and self-linkage, in the case of self-linkage for antiparallel reconnection, we can think that any change in helicity must be solely due to a change in intrinsic twist. And this poses further emphasis on the fact that we have to focus on the internal structure. This is a more recent simulation of reconnection where you see only part of this reconnection. The blue tube reconnect with the red tube into this hairpin filament or tubular form, and we have to focus on the internal redistribution of twist upon reconnection. Okay, I now want to move, having said something about the role of writhe and the role of twist under reconnection, I want to consider a situation where filaments are more complicated than the simple vortex ring or helical vortex or the straight vortex, which are the only three cases where we have some mathematical results, remember. Okay, well, defects, vortex defects in condensates and vortex filaments in superfluids have been more intensely studied in the last 20 years or so. This is a beautiful picture of a sort of complex networks of these defects in a uniform background situation. And here is the presentation by Carlo Barenghi. We are in China, in Beijing, a year ago, and Carlo presented this new and collaborator. Here is Rob Sharine, author of NotPlot software that is used very much by many of us to talk about knots and links. And we have here the presentation of the fact that doing simulation of a turbulent tangle of filaments in superfluids, he was able, the group of Carlo were able to extract a number of elements showing knottedness and linkage. And knots were found to a great degree of complexity. By great degree of complexity, I truly mean enormous knots with polynomials degree of the order of 30. So well beyond any classification we have so far. And this picture is a little bit, there is a little bit of a romantic me thinking when Keith Moffat told me when I was young that no such knots could be found in any fluid because of the role of viscosity. They would have made them so immediately evanescent. Well, here we have the proof that structures indeed may not last long, but they can form and have a great deal of complexity. That gives us strength to move on and consider that helicity may not be sufficient to describe topological complexity. Well, helicity, remember, as I showed you so far, is function of strength, so there is some information about physics, and topology through linkage. But we know the limits of the linking numbers. Indeed, this was recognized as early as 1867. This is an original drawing of Maxwell, who pointed out, you can read it in his second volume of his treatise on electricity and magnetism. He has a section on Gauss linking formula derivation, by the way, rediscovered or proposed by himself independently, because Gauss didn't give us any proof of the fact that the linking number is a topological quantity. Very remarkably, Maxwell says, yes, he is a strong invariant of topological character. However, for Borrmean cases, or what we would call Maxwell link, that somehow for the twist of history are called the weighted link, they still, linking number is still 0. So linking number is a good topological detector, but not as good as we would have wished, because it cannot distinguish a situation that is displayed here. 3 unlinked loops, 3 linked inseparably linked loops, and 2 linked filaments. All these 3 systems have linking number 0. So not only the problem is with relative linkage, but we may have linking different from 0, but total contribution from linking number 0. And that means that if these 2 quantities are 0, then evidently helicity is 0, despite of having a topological complexity present in the fluid. So next step is as obvious as a history of knot theory would suggest, to go to knot polynomials. And this is the piece of work Xin Liu from Beijing and myself have embarked to do. Now, before showing the result, I want to use this half a slide to do a recap of the polynomials, a knot polynomial. And I pretend very arrogantly for half a slide to give you the essence of knot polynomial theory. Okay, I will refer to HOMFLYPT polynomial. It is a polynomial in 2 variables, and for the moment, for this slide, say, no physics is concerned. So let's pause for a moment about physics, and let's focus on knot theory. HOMFLYPT is an acronym coming from contributions from several authors, including the person who taught me knot theory in Cambridge, Licorice, and then Krzyzewski, Trakczyk, and then Millet, and Okeanu, and other, Hoste and Yete. Anyway, this is a polynomial introduced more or less in the late 80s, and following Jones. And we have to use 2 skein relations. In other words, 2 relations to define a polynomial. This polynomial is finite terms Laurent polynomial. The first relation is trivial. It says that the polynomial of the unknot is 1. Okay, that's easy for me. The second relation says that if I switch a given crossing by considering, say, your preferred tangle, you choose an element, you extract an element, a component in your tangle, you project it on a diagram, any diagram, because remember, this polynomial is going to be a topological invariant of the knot or link we consider. For instance, in this case, the picture shows an unknot, because there are, you see an overcrossing here, an overcrossing here, and an overcrossing here. So it actually is an unknot, it's not a knot. But anyway, we consider the diagram, we put algebraic signs, plus, minus 1, on these crossing sites according to some sign convention, and then we have to consider switching the crossing, 1 crossing at a time, any crossing we choose, from an overcrossing to an undercrossing, or the other way around, and put it in relation to a smoothing. Well, in words, it sounds complicated, but let's do an example. So the example is as simple as it can be. Let's start with the unknot. And I know what you're thinking. Well, the unknot, come on, Renzo, I know the unknot. The polynomial of the unknot is 1. Yes, good guess. So the unknot can be deformed. For example, in this figure of 8, I call it gamma plus because there is a positive crossing apparent here. And of course, is equivalent to a gamma minus, negative crossing apparent here. But all 3 are the unknot. And so the polynomial of these configurations is 1. Okay, I use just this relation, no use of the second relation. Now I want to use the second relation in the most simple possible form. So I start with the unknot again. I know the polynomial of gamma plus is here, is 1. But then I want to apply this second relation to the only crossing that is visible in the diagram is this. And so I switch the crossing, as you see here, I switch gamma 1, gamma plus into a gamma minus configuration. And then I want to use the smoothing of this crossing so that the crossing disappears magically. As I said, this is just pure mathematics. There is no physics. And then I get, as a result, by smoothing the crossing, I get U2. This is a new configuration, new topology, because U2 represent two unknotted links for which I do not have a polynomial. Indeed, I can find it by applying this second relation. You see, the polynomial of this configuration, gamma plus, is known, is 1. So I have A times 1 minus A minus 1 times the P of gamma minus is also 1. So minus A minus 1 equals Z of the polynomial of U2, which I don't know. So I get the P of U2. And this is the polynomial of this new configuration. Okay, well, by now you have on Knot Atlas and many websites, you have all these polynomials worked out for all sorts of knots up to a number of crossing that I don't remember now is say probably 10 or maybe some 11 links as well, of course, not only knots. Here, let me go immediately to the bit of physics. And we have a result that I'm not going to prove it because it's pretty elaborated and you can read it in the paper, and is the following. If K denotes a vortex knots of axis C and helicity H of K, then E to H of K, so E to this form of helicity that I showed you before in case of localized vorticity to thin tubes appropriately rescaled, of course there is a gamma circulation there that is not present, satisfies under plausible statistical hypothesis the skin relations of the HOMFLYPT polynomial. It is very important because we can express this polynomial HOMFLYPT now in terms of some physics, and I show you what I mean by that. Well, first of all, we can interpret these polynomials in terms of the quantities that I mentioned before, writhe and twist. Somehow we can relate A and Z, the two dummy variables that we had before, as just pure variables in a mathematical expression. Now we can express them in terms of, twist and writhe. And so we can express or interpret physically the second skin relation as a relationship between writhe and twist. And more importantly, we have Jones polynomial around, and we can interpret the skin relation for Jones polynomials, and in particular, since HOMFLYPT is a polynomial of two variables that can be reduced to a polynomial of one variable to Jones, we can interpret this reduction in terms of the framing of the Jones polynomial physically, in terms of a relationship, strict relationship between writhe and twist. Okay, what that does tell us in terms of vortex knots. Okay, let me be a little bit more specific. So first of all, notice that by doing this transformation, we have a polynomial HOMFLYPT that is now adapted to our physics, so it becomes a function not only of linking number, but of the knot type itself, and the contribution from physics through gamma. Now, let me do an example. This is a very, very simple example. It's not based on experiments whatsoever, so take it for just a simple illustration of what I mean. Well, we have here some constants, don't pay attention to this, but the end result is that A and the Z before can be related to writhe and twist. And for simplicity, I take average writhe and average twist in a tangle as a half, and then there are coefficients that are related to the statistical approach we did in order to recover our formula. So end result is that the Z becomes this expression, and A becomes this expression. In other words, we can give numbers to these variables. So the polynomial not only distinguish knots with, of course, fully topological invariant. It has drawbacks as linking numbers have, but in other words, not only can distinguish knots qualitatively, but can distinguish knots quantitatively, because we give numbers to these expressions. So an ensemble n number of unlinked, unknotted loops un as a polynomial value that is this number. And notice it diminishes with increasing n. Okay. And then if we go to the knot table, we have the standard HOMFLY polynomial for the positive Hopf-link. And if we use this approach and use this number, we have this polynomial. So the polynomial of the negative Hopf-link has a different value. The left-hand trefoil knot, this value, the right-hand trefoil knot, the figure of 8 knot, the whitehead link, and so on and so forth. Can we make any sense of these numbers? When we got these numbers first time, I was very puzzled because we cannot, or we couldn't recognize any order in that. But if we go to the experiment of the trefoil vortex filament, we see that there is, through a sequence of reconnection, we start with the trefoil, we have a single reconnection that makes us, give us a Hopf-link, and then the unknot, very convoluted in space, but is an unknot, and then eventually 2 separate links. Well, I'll be very brief here, but we can think of these are all these knots as part of a bigger family of torus knots. So knots drawn on a mathematical torus, as more or less the shape I showed you here in the diagrams. We did with Simone Zucker, who has a very, very nice code for vortex defects in Bose-Einstein condensates. He performed an experiment. At the time, we couldn't start from the trefoil, now we can. And at the time, in this paper 17, we published these results starting from the Hopf-link, but we could push the cascade to 3 links. So you see, again, we have an Hopf-link, the unknot, 2 separate links, and eventually the formation of a 3rd link through single reconnection events. Now, this suggests the fact that we can assume a single antipole reconnection event takes place at a time, and a family of torus knots and links that are formed by producing a reconnection at each time on a strand, on a pair of strands, so that we go from, say, the torus knot 2,7 to the link 2,6 and knot 2,5 and so on and so forth, till the formation of separate rings, eventually 3, 4, etc., etc. And then we can apply our theory to this sequence. So let me tell you that the result of this is very nice. We get an expression, a mathematical expression, in terms of functions of twist density and writhe density. And these functions are totally known. So we can compute numerically these functions for all the sequence of torus knots and links we see here. And when we do this, we saw that the numerical value for the HOMFLYPT polynomial for the trefoil is 150. Remember, now we have an exact information of the writhe and the average twist present. Let's say the average writhe and total torsion present. And then 1/5, 1.5 goes to 1.48. So we make sense of this cascade now in terms of topology as well, a quantified topological cascade. Now, the sequence is present here. for this assumption, I just made a very brief remark saying that if we make different assumptions on these numerical values by assuming different values of writhe and twist the present, for the same class of torus knots, we find the same monotonic decrease. Maybe we have a shift in the vertical axis of the values, but the same monotonic decrease is confirmed. And this is consistent with a very simple analysis, for example, here done on the bending energy, curvature energy of these structures and other energy types consistently. Well, if we compare the numerical values by our approach done similarly for Jones or other polynomials, we find that at least for numerical purposes, HOMFLYPT seems to be a good marker for these structures. Although I have to say that Alexander polynomial was used recently by Carlo Barenghi and proved to be pretty good as well. So this is really research ongoing. Let me conclude. We proposed to use adapted HOMFLYPT polynomial to quantify topological cascade of vortex structures, and this proves to be the best quantifier because, as I showed you here, the difference between one topology, one knot type, and the other is well marked and probably easier to capture in a numerical analysis in diagnostics. And this is consistent. This is consistent. By the way, also interesting is to compare the rate of change in time of these differences, not only considering this cascade progress, but other different types of topological transitions. And this is a piece of research that is now going on with Shin. So in summary, the polynomial provides a monotonic behavior consistently. The numerical values are robust and reliable markers for possible diagnostics. And as I said, for the few knots that I showed you, there is a way to estimate the transition between one and the other, and this transition rate is more or less constant for the class of knots I consider. But of course, this is a very specific case. It's interesting to notice that a very actually identical cascade has been found in 2013, same time of William Irvine's work in DNA plasmids under recombinant action of site-specific enzymes, on which I'm sure Dewitt-Sumners will spend a few words because it brings a very interesting connection with our case or the case of reconnection of magnetic structures. But as I mentioned, would that path be unique? Well, certainly not. And would that path be optimal? Well, optimal. Optimal in which sense? Well, there are many ways to define what is an optimal path to cascade in terms of energy, in terms of topology. I don't know. Well, there is a possibility, for example, that one of these knot types, the torus knot 2,5, may decay to form a deconnected sum of the trefoil and the Hopf-link. And if we were going towards this other route, we would find that our numerical values would equally decrease monotonically. And so we are puzzled by the fact that maybe our polynomial approach is useful to quantify these transitions, but would that be useful to select the best possible path? Of course, in terms of energy, that means, in other words, in terms of entropy and disorder. And this is a piece of research that is ongoing, not only by us, by other groups, not many. And we are confident to be able to show you some new results in the in the year to come. Let me conclude here with just a selection of references so that everybody can inspect the papers I mentioned, and I apologize if I refer to my own work mainly, but I think that is consistent with the talk. Thank you very much for your attention.
Thank you.
Okay, thank you very much.
Thank you.
So thank you very much for beautiful talk, and please questions.
May I ask you one?
Please, please.
Okay, Renzo, could you tell us, do you have always torus knots, or this is not obliged?
No. This is not obliged at all. Well, of course, maybe for some reason, remember the picture of Lim, the movie, the experiment of Lim, who, by the way, is carrying out right now numerical work on the very same experiment he did in the 90s. Well, for some symmetry reason, etc., they might be the ideal cascade processes, but not at all, not at all. We all know that fluid structures are far more complicated than forming knots and links, and they may form complicated knots, as I showed you in the work of Carlo Barenghi's group, by the way. I like, if I can go quickly to that slide, I like to advertise his result, because it's quite nice. And indeed, they found very complex knots. Not at all, you see here. Mm-hmm. They got the knots, they have the data from the numerical simulation, so they can somehow go backwards in these from these incredibly complex configurations. And that is done with the help also of Ropshire-Hines knot plot and other relaxation techniques that they employed. So you have a configuration that is extremely complicated. You extract your data, and with some software, you relax it, so to speak, so that you can recognize the knot type. Once you have the knot type, you have to do another process. You have to implement these polynomials in order to either identify the knot type through the polynomials, or give numerical values to this polynomial to eventually to assess the approach we offer.
I'm asking that because just some remark that if you would stay only in torus knots region, so then probably you know that there is some work which can identify the HOMFLYPT polynomial of torus knots with a Dick path, one-dimensional, very simple Dick path, when you fix the area below the curve. So there is very nice interpretation due to Gorski and others, but unfortunately this is not much explored by physicists.
Well, I know, I thank you, Sergey, for pointing out that, because I know you've been doing work on that too, and thank you, by the way, for pointing out that work to me, and is indeed a very interesting area of research. Clearly, if you confine to, say, the torus knots class, then your mathematics, at least in my case, is simpler. By the way, I can't remember if I did it in my last slides, but we just finished a piece of work that has been published recently with sorry, I just went out of Chiara Alberti. So the relevance, the effects of winding number of different knot types, and that is done in the context of vortex dynamics, ideal vortex dynamics with Biot-Savart and desingularizing Biot-Savart. So that is a piece of work you find at the end of the selected references I gave you. And in the case of torus knots and links, of course, by symmetry, you can make some progress. Otherwise, it's clearly very difficult.
Yeah.
Okay, thank you. So please, more questions?
Renzo, may I ask you to send your slides? If you don't mind, I would upload it on the website of our conference.
I am very happy. I have to tell you very honestly, very rarely I show references at the end of my talk because it's so, you know, self-promoting. But because of this, I think it makes sense to have also the slide of references to help young people. So with pleasure, I will send you the compressed file, hoping that is not above maybe 8 megabytes or so, and certainly Nikolai. Yeah.
Excuse me, Renzo. Can you see this in your cascade, the transition to chaotic behavior?
Well, not well. Remember, our approach is so simple and so initial that that what you suggest is in my mind, but I cannot say that I've done any work.
Like Dragonbaum stuff, something like that.
Yeah, sure. But if, well, you provoke me because I know you are a very creative mind. And for those creative people, I can say, I mentioned very briefly in the stating the theorem with Xin-Liu on the adapted polynomial that we used some simple statistical assumption. Now, of course, in this statistical assumption, the implication is that there is no preference, particular preference during reconnection. We take, you know, the smoothing of the crossings as possible isotropically in all directions. But you may have systems, indeed we have systems in statistical mechanics where you may, you know, insert particular rules. And so if you insert particular rules for reconnection, for example, anti-parallel forcing, anti-parallel reconnection, taking care of the writhe conservation proved by DeWitt and others that I mentioned, etc., etc. If you do that, you can revise these numerical values in light of these assumptions. And that I think is worth doing. But of course, it's a piece of work. And you go far beyond that in thinking, of course, of chaotic behaviors. I think would be, it has been in the past, and maybe now after 20 or more years, is again time to push people in dynamical systems to do this, study. Because they did it in the, you know, in the maybe in the 80s, 90s, but now I'm not so sure. So it's good time to have them on board with us, of course, for this big problem. Thank you.
Okay, thank you very much. So more questions, comments, remarks? Seems no. So thank you again. So
thank you, Andrei.
Beautiful talk. Thank you very much.
Thank you. Thank you to all of you, and all the best over there in Novosibirsk. Bye-bye. Say hello to Sergey. Say hello to Sergey, Alexienko, and Pavel Kubin and all the group over there. Thank you. Thank you. Bye-bye.
Ciao.
Bye. Ciao. Ciao. Stay safe.
Ciao.
You too. Okay. Thank you very much.